So last time we talked about the different architectures, okay, of the CNN, okay, including such as ResNet, right? So the only thing that we haven't finished is the last one, which is the SENet, this one. Okay. So the SENet is the winner of 2017 challenge. Okay, the SE stands for squeeze and excitation. Okay, so why this architecture gets this name? Okay, we will describe. Okay, later. Okay, so the most important concept of this SENet is in the SE block. Okay, this SE block can be used along with such as the inception module as well as the residual block. Okay, we will describe later. Okay, so basically this SENet, okay, the concept is very simple and it can be used to improve different kinds of network architecture. So this is like one of the important concept. Okay, just like ResNet. Okay, ResNet also like is one of the important concepts like proposed in these network architectures. However, okay, I'm not sure if you guys are familiar with the attention mechanism. Okay, the attention mechanism, in somewhat is similar to SE block. Okay, we will describe this. I mean later. Okay, so basically, okay, this if you use this SE block along with the exception or the ResNet, okay, the performance, okay, the top 5 error rate of the ILS VRC ImageNet competition, okay, it will be as low as 2.25%. So this is a big jump, considering like the year before this one, okay, the one that is proposed by the Hong Kong Chinese University, okay, their result is only slightly below 3%. So this is like more than like well, because from 3% error rate to 2.75%. Okay, well, yeah, 2.25% error rate. So this is like what should I say, like close to 30%, right? 25 to 30%. Yeah. Well, yeah, I think it's a 25% improvement. Okay, over the top 5 error rate. So this is like a big performance gain. Okay, so what is the SE block? Okay, how does it be used along with the other module? Okay, so this is the idea. Okay, for example, when the SE block is used with the inception module, okay, you have the inception module output, okay, the original output, and then you have the same output that goes through the SE block, and along to multiply with the original output. So this SE block basically, okay, determine certain important factor of the output of your module. Okay, for residual unit, it's the same thing. Okay, you have the SE block to go with the residual unit after the residual unit, and then the output of the residual unit is multiplied by the output of SE block to sort of determine which part is more important. Okay, so you can see the words that I'm using here. Okay, which part is more important? So it's kind of like you should put. I can change the sentence into like where you should pay attention to. Okay, for the output of these modules. Okay, so this is very important because this goes one step closer to the attention mechanism. Okay, so let's have a closer look of this SE block. Okay, this SE block analyzes the output of the unit it is attached to. Okay, and it will focus exclusively on the depth dimension. So it does not look for spatial pattern. So as a result, okay, it only check which, what should I say, which feature maps are more important than the other. So it learns which features, which feature maps are usually most active together. Okay, if it then use its information, okay, to recalibrate the feature maps. Okay, when we say recalibrate, I mean like well, here we want to say to emphasize certain feature maps, but in reality we don't emphasize that. We sort of like discount those unimportant feature maps, okay, to achieve the similar effect. Okay, so for example, okay, an SE block may learn, okay, for example, like when you try to recognize a face, you'll see like a mouth, a nose, and the eyes, okay, normally are together, okay, in picture, for a face. Okay, so if the if the feature maps of the mouth and nose are active, okay, then we should see, we should expect, okay, the feature map for the eyes to be active as well, right? But if for any reason, okay, if the feature map of the mouth and nose are active, but the feature map for the eye is not active, so what this SE block is going to do is, it is going to you'll boost the eye feature map, but in reality it doesn't do that. It actually will reduce the irrelevant feature maps, sort of to achieve the similar purpose. Okay, so if the eyes were somewhat confused with something else, okay, which may occur like in certain scenario, okay, then this feature map recalibration, okay, will help resolve this ambiguity, and which also help you to better recognize the object, obviously. Okay, so it's something like this. Okay, so let's assume, okay, the darkness represent of this feature map represent like how active each feature map is. Okay, the lighter the color, the more active the feature map. Okay, so you can see, okay, the most active feature map are the third one and the fifth one, right, from the top. The third one and fifth one, because they are pretty much white, right? And you see, we can assume, okay, these two represent the mouth and the nose. Okay, assume that the second feature map represents the eyes. but for some reason, it is not as active as the mouth and the nose one. Okay, so what happens is that, okay, after you go through this SE block will compute a vector like this. Okay, and then it is going to multiply each of these feature map by the corresponding number in this vector. So it's going to multiply the first feature map by 0.0, the second feature map by 1.0, the third one 1.0, the fourth one 0.3, the fifth one 1.0, the last one 0.2. So as a result, okay, you can see except the mouth, nose, and the eyes feature maps, the other feature maps are, they become inactive, right? They become inactive. Because of that, okay, so the active level of the mouth, nose, eyes feature maps are sort of like, I shouldn't say strengthened, but in contrast, it is much more easier to identify, right? Okay, so this concept actually, because I don't think in this class we will have time to talk about. I mean, there's a chapter that is dedicated to the NLP, which will talk about some concept in NLP, which includes attention. Okay, but unfortunately, I don't think we have time to cover that chapter. Plus, in our department, we already have a professor who teach the NLP. Okay, it's Professor Cai Zhonghan. Okay, so I will refrain from stepping into somebody else's field. Okay, but the concept of putting more attention to the area that is should be focused on. Okay, this is exactly similar to attention. Okay, so how does SE block come up with this? Okay, so SE block is composed of just 3 layers, very simple architecture. Okay, a global average pooling layer. This global average pooling layer is going to reduce each feature map into one number. Okay, a hidden dense layer using ReLU activation function. Okay, and the dense output layer using sigmoid activation function. So because it uses sigmoid activation function, so the result of this dense layer output is going to be in between 0 to 1. So it's going to become, numbers like this, between 0 to 1. Okay, but how does this 2 dense layer able to accomplish that? Okay, so first, I mean, from this, hopefully you understand. Okay, the second term in the SE block. Okay, the excitation, because it make the important feature map excited, right? Okay, so this is like the excite. Okay, excitation part. Okay, but what is the squeeze? Okay, so this is the squeeze. You see, the global average pooling, as I said, is going to convert all the feature map each feature map into one number, right? Say if you have like 128 feature maps. So after this global average pooling layer, you are going to end up with 128 numbers, right? Numbers. Okay, but this information is going to go through this dense layer, and in this dense layer, okay, you can see that we intentionally draw this layer to make it much narrower, right? Much narrower. This layer is normally 16 times smaller than this layer. Okay, if this is 128, divided by 16, it's going to be what? 8? Okay, if it's 256, then this one it will be 16. Basically, it's like 16 times smaller than this global average pooling result. Okay, so this is where the squeeze happens. Okay, we want to, squeeze this output to, how should I say, like, to make it the embedding. Okay, the embedding is pretty much like a dimensionality reduction concept. Okay. We actually will talk about this concept later in the autoencoder, but since I'm not sure if we have time to talk about autoencoder, because it's already December, right? So we only have how many lectures left? 3, 4? Because the last lecture of the December is going to be final exam. Okay, today is December 1st, right? Yes. So we have another 4 lecture and then the final exam.
And then the report.
The report.
The presentation.
Presentation. Then we have 3 lectures left, including today's one. We have 4, right? Let me check.
Including today, we have 5.
We have 5. Yeah. So we only have like a. Let me double check. The first. Where is the first 1号、8号、15号、22号. Yeah. Excluding today's lecture, we only have 3 additional lectures left because the last one, the last lecture in December is going to be a final exam. Okay. So yeah. So I would just describe like what is the concept of embedding. Okay. Embedding means like you try to represent something like that is like a higher dimensional into something with a lower dimension. For example, okay, if I start giving you a sequence of numbers, okay, say 5, 11, 2, 4, 21. So if I start giving you like these numbers, like in random, it is very difficult to memorize, right? And you need much higher dimension to memorize all this information, right? You need a lot of storage. Basically, you need as much storage as the number of these random numbers that I'm talking about in order to memorize all of them, right? This is obvious, right? Okay, but if I tell you, okay, something like this, okay, well, 2, 4, 6, 8, 10, 12, 14, 16, 17, 18, 20, if I give you these numbers, it's very easy to memorize, right? Why? They are both numbers, right? Okay, you can memorize that because, well, obviously these may represent the even numbers greater than 2, greater or equal to 2, right? Okay, so or if I give you like maybe 2, 3, 5, 7, 11, all this, these obviously they are prime, right? They are prime numbers. Even though it may take a little bit more description for to describe, okay, the concept of prime number, right? But still, it requires much lower dimension to memorize what I'm saying, right? Than to memorize every number, right? So there are a lot of examples like this, okay? for another example, okay, is like you guys have learned English through like especially English vocabulary through memorizing, right? So basically, like if you do not have any particular system to memorize every word, then you do need to memorize every English word like very hard, right? Okay, but if you after you learn English for, well, I mean, you guys are now like at least like in college, so you have learned English for more than 10 years, right? So okay, you understand like the English word actually has structure, right? It has prefix normally. It has like the core, okay? It has like maybe postfix, right? For example, like if you see any like tion, it means something noun, right? Right? It's a noun. If it ends with tion, or if it ends with al, it means it's an adjective, right? So you know that, right? Or like for example, like if you see bi, start with bi, that means normally means like something twin, right? Okay, you have two of something, right? For example, binary, right? I mean, which is the most common word that we use in computer science, right? Binary is 0 and 1 because it's two numbers, right? Okay, we have like so binary, this type of thing, okay, pretty much means like a prefix. They give you like a certain meaning, okay, for the prefix. Or like the tion pretty much gives us like a certain meaning for the postfix of the word, right? So basically, like if you learn English in certain structure, it will become much easier for you to memorize English words, right? Okay. It's similar to the example I just told you. Okay, originally, if you do not have any type of these structures, basically you need to, you will have hard time memorize every word because it requires you to have a much higher dimension to memorize these words. But once you are able to identify these structures, it helps you to memorize things in a much systematic manner. Right? Okay, so this is something like this. Okay, so originally, okay, the information says 256. Okay, because you have 256 feature maps. So when it goes through this global average pooling layer, it becomes 256 numbers, right? So that's 256 dimension, right? 256 dimension. 256 dimension is a lot, okay? It's a lot. But in reality, normally, okay, when you have a network, what you need to memorize is, what you need to be able to recognize doesn't require that much higher dimension. Okay, for example, okay, remember like this, we are talking about the ImageNet competition, right? So ImageNet competition, how many classes do we have? Only 1,000, right? Only 1,000. Well, it's a lot of classes, but in terms of number of classes, it's not that much. Not that much, right? Not that many. So okay. So once we reduce it to 16 dimension, that's good enough. It's just like okay. For example, so remember like the example I had earlier. Okay, the mouth, nose, and eyes represent a face, right? So now originally, okay, we have 3 different dimensions in the feature map to represent different features. Now, okay, because of this is squeeze. Okay, we squeeze these 3 dimensions into sort of squeeze these 3 dimensions into one. To say, oh, this is face. Okay, this is face. So this is the squeeze. Okay, it will squeeze like the higher dimension information into the lower dimension one. In neural network area, okay, we call such information, okay, lower dimensional information as embedding. Okay, and with that, then we will have another layer of dense layer, but this dense layer is going to become 256 again. Okay, it's going to convert this embedding information into the 256 numbers. I mean, between the each one between 0 to 1. Okay, that we're going to use that. Okay, to excite different visual maps. Okay, that's the concept. That's the concept of SE block. Okay, it's a very interesting concept and a very powerful one too. And actually, it can be applied to different network architecture. Okay. Sorry, it's not. Okay, so I think I have gone through all this already. Okay. So basically, we finish all the famous CNN architecture. Okay, and now we are in a position to demonstrate how we can implement one of the famous CNN architecture using Keras. Okay, you will see that it's actually very, very easy. Okay, to use Keras to implement one of the famous architecture. For example, ResNet 34. Okay, this 34 means if you still remember, we say the number here represent the total number of layers, including dense layer, including convolutional layer. Okay, yeah, but not like the batch normalization, those stuff. Okay, so we need to implement this. It's actually very simple. Okay, so first we implement a residual unit class. So this in here we actually remember the Keras has several ways to implement the network, right? One is like a sequential API, but obviously sequential API doesn't apply to residual unit, right? So we do need to use something else. The second one is to use the functional API. The third one is to use a subclassing API. Here it's more like we use the subclassing API for the residual unit. Okay, so this residual unit is a subclass of the layer class. And if you still remember the subclassing API, basically in here we define what layers, what layer we need to create. So here you can see that we create one convolutional layer, and pretty much remember I told you after the Google net, every convolutional layer we have a batch normalization. So this goes without saying. And then we have another convolutional layer and batch normalization. For most of the residual unit, basically the size of the feature map stays the same, and the stride is 1, and the padding, the feature map, the kernel is 3. Okay, so this is but as for how many feature maps, we will wait for the we will use it as a parameter. Okay, which will be determined later, because different residual unit could have different feature maps. Okay, so we will determine that later. But once a while, okay, we do need to reduce the we need to reduce like the size of the feature map by using the residual unit. Remember? So okay, here okay. If stride greater than 1, so stride is pretty much also a parameter that is passed through this construct. Okay, so if stride is greater than 1, so then we have to create 2 additional layers. These layers, okay, will be used, as for the in the skip connection, okay, because in the skip connection, when you reduce the size of feature map, that means like in a skip connection, you also need to have it go through like this convolution layer to reduce the feature map in order for them to to be added together. Okay, so you see the stride is one filter. So these are nothing pretty much to talk about. And in the core, this is where we determine how these layers are connected. This is where we determine how these layers are connected. So first, okay, we basically put these layers in, just use this loop to put them together. Okay, and then we have a skip connection. So in this skip connection, so we put this there, okay, appropriately, and that's it. That's it. So this is like a residual unit layer class. Okay, and then okay, we build the ResNet 34 by you calling that a residual unit class. But of course, at the beginning, I forgot. I don't think you guys still remember. So where is it? Here. Okay. It's something like this, right? We'll have to go through this first, and then go through a number of residual unit. And last, we have an average pooling layer and the fully connected layer as output. Okay, so it's kind of simple. So, but of course, for these few layers, input layer, these few layers, they are just regular layers that we can create. What the residual unit class is going to help us to create, this part. Okay. So come back to here. Okay, you see. So here we, once we have the residual unit taken care of, okay, we can use the rest of for the rest part of the network, we just use sequential API, because the other part does not involve like anything that cannot be done by the sequential API anyway. So first we have like one layer, okay, the convolution layer, okay, 64 feature map, kernel size 7 by 7, stride is 2, okay, the input shape is 224 by 224, and it's we have 3 channels because it's a colored image, okay, and the pattern is same, okay, so, and then with a batch normalization. Remember, for every convolution layer, we have a batch normalization, okay, and we add the aggregation function to be rerule, and then max pooling, okay, so I don't think I need to explain a lot here. So then, okay, here is the interesting part, okay, we have a loop here. For filters in 64 times 3 plus 128 times 4 plus 256 times 6 plus 512 times 3. That means we need, how should I say, like we need totally 3, 4, 6, 3, 16 residual unit. Okay, each residual unit, the size is specified like this. For example, at the beginning, we need 3 residual units of size 64. So, okay, so stride is 1 if the filter equal to previous filter. So we intentionally set previous filter to be 64. So now the filter size is 64. So 64 equal to 64, then stride is 1. Otherwise, stride is 2. Okay, so we call this, okay, to add a residual unit. Okay, and we pass the number of filter, the stride number to it. Okay, and then assign this filter to the previous filter. So the only time we change the stride from 1 to 2 is, when it is, the number of feature map change from 64 to 128, or to change from 128 to 256, or change from 256 to 512. Okay, and in that case, we are going to include this one. Okay, because at that time the stride will be greater than 1, and we'll include this one as the layer in the skip connection. Okay, so we have this loop to deal with all the residual unit. So after that, okay, we have to go through the global average pooling, flatten the result, and then, well, we add a dense layer, okay, with softmax elevation, and we are done. So it's you can see it's a very, very simple to create a ResNet 34, okay, from scratch. Okay, it is actually as easy if you want to create even larger ResNet, okay, or some other classical CNN architecture, okay. But however, okay, so the explanation, I think I would just skip that. So you can see it's amazing. Just fewer than 40 lines of code, we were able to build the model that won the 2015 challenge. Okay, so it can basically showcase that how elegant the ResNet model is, and also showcase like the expressive power of the Keras API. Okay, so so we can implement some other architectures as well, but here we just show you an example. But in reality, in CNN, we normally never train the model from scratch. We normally use transfer learning. Okay, you won't have to implement standard models from GoogleNet or ResNet. All these famous CNN architecture can be, their pre-trained model are available, okay, in Keras.applications package. For example, okay, if you want the ResNet 50, so you just, use this line, okay, Keras.applications.resnet50.resnet50 with, you can specify, the pre-trained, pre-trained parameter is used in this model. If you specify, okay, the weight is equal to ImageNet, that means this model is pre-trained by ImageNet. There are other, parameter you can set, okay, for this model, okay. So that's it, okay, and of course, like so ResNet 50 model expect 224 times 224 pixel image. Okay, so if your size, if your input size is different, then okay, what do you do? You can use TensorFlow tf.image resize function to resize your image so that it fits into the 224 times 224. For example, here is the example, okay, that you call tf.image.resize images, and you specify like what size you want it to be, okay, the result is, just give it to this this one. But sometimes the image the width and the height has special ratio. Okay, for example, like if most of the you see like the 256 by 256, 224 by 224, this is pretty much square, right? Square. But if your image are not square, then maybe like they are long, okay? And if you resize it to 256 by 224 by 224, the objects in your image may be distorted, right? So what do you do? Okay, you can crop it. You can crop it and resize it in order to make sure your image, okay, the object in your image does not will not be distorted. Okay, so there's a function called tf.image.crop and resize that can help you to do that. Okay, but I will not go into detail. But you get, I mean, if you need to use that, you can check out the API and use it easily. Okay, and also if you use the pre-trained model, okay, the pre-trained model sometimes assume the image are pre-processed in a certain way. Okay, so in some cases they may expect the inputs to be scaled from 0 to 1 or from -1 to +1 and so on. So how do you know, okay, what format this pre-trained model is, right? So actually, okay, for pretty much for every pre-trained model, okay, it comes with a pre-processed input function, which can help you to pre-process your image into the format that is required by this pre-trained model. Okay, so for example, okay, remember that ResNet 50 model. Okay, if you want to use that pre-trained model, okay, then we can use Keras applications that ResNet 50 that pre-process input to, and you feed your image into it. Okay, because originally, okay, this pre-processed input expect the pixel value from 0 to 255. So we have to, because after the image is resized, actually the original image value is between 0 and 1. So we multiply this by 255 to make sure this each pixel in this image has a value from 0 to 255. And then use this pre-processed image to, input to make sure it is complied with the pre-trained model. Okay, and then you can use it for prediction, anything, pretty much. Okay. Well, yeah. So let's take 10 minutes break. When we come back, we'll continue our discussion here. Okay.